going to talk about symmetry, starting on page 650. So on page 653, we're going to have these two learning targets, or excuse me, one learning target with two parts. We're going to identify line and rotational symmetries in polygons. So we're going to identify line symmetry, and we're going to identify rotational symmetry in polygons. And let's see what our definition of symmetry is. So at the top of page 653, it says a figure has symmetry if there exists a rigid motion, reflection, translation, rotation, that maps the figure onto itself. Okay, so symmetry gives you one of those rigid motions to give you the figure onto itself. And one type of symmetry is line symmetry. So that's our first learning target, to be able to identify line symmetry. All right, and this key concept then says that a figure in the plane has line symmetry, which can also be called reflection symmetry, if the figure can be mapped onto itself by a reflection in a line. Okay? Now, so if this is line symmetry, then the line of reflection can now be called the line of symmetry. You can also call it the axis of symmetry. And here's how this works. If we look at our figure over here, we'll see that the top parallelogram could be reflected in this line and become the bottom parallelogram, and vice versa. So the figure as a whole, the chevron-shaped figure, has line symmetry because with this line of symmetry, it reflects upon itself. Okay, because the top reflects and becomes the bottom reflects and becomes the top. So a reflection maps the figure onto itself, so it does have line symmetry, and then the line of reflection, the red dotted line there, can also be called the line of symmetry. Any questions? Well, let's take a look at some examples. And these are real world examples, by the way. That's pretty fancy. So if we look at this crab here for example A, well, let's read the directions. State whether the object appears to have line symmetry. Write yes or no, and if so, copy the figure, draw all lines of symmetry, and state their number. I won't make you copy this down, but let's just look up here at the screen and see it. So, does the crab appear to have line symmetry? Yeah, it does, okay, because this line right here appears to, well, let's put it this way. The left side of the crab appears to be identical to the right side of the crab. So the left side would map to the right side would reflect to the left side. So yeah, it maps the figure onto itself. So yes, it has line symmetry and just the one line of symmetry. Then if you look at part B, the starfish has a lot of lines of symmetry. So let's look at a couple of these. Like this line right here that I've made red, okay? Putting the left side to reflect it and become the right side and vice versa. Or notice one like this, couldn't the top part be reflected and become the bottom part and vice versa? So is it real surprising that since the starfish has 5 arms, tentacles, arms, that there would be 5 lines of symmetry? Yeah, probably not that surprising, right? So crabs have line symmetry. They're symmetrical. Starfish are symmetrical. What about an oyster? No, it doesn't look like it. We can try to draw some lines in here if we want, okay, but the two halves don't look identical by any stretch, do they? Maybe if I did one like that. I'm getting closer there, but still no. Okay, not quite. So the two halves of the oyster shell never get reflected to map onto each other. Okay? So, once again, any questions? Let's see whether or not you should have asked some. So turn with me to page 656, and let's do these first 3 together. The directions say to state whether the figure appears to have line symmetry. So we'll write yes or no, And again, I won't make you copy the figure, but I want you to be able to state how many lines of symmetry there are. And the only reason I'm telling you not to copy, that you don't have to copy the figure, is you probably won't be able to duplicate exactly what's in the book anyway. Okay? So, number one, what do you think? Does that have line symmetry? Mm-hmm. Okay. Now, I'll go ahead and draw them so that we can count them. How many lines of symmetry do we think there are? That'd be one, wouldn't it? Okay. So one. Yeah. Two. Is that it? Three. Yeah. If that one's one, then I've got to be able to do that, don't I? So four. Okay. Using any of those as a line of reflection, the figure would map onto itself. So yes, there's line symmetry, and in fact, there's four of them. What about number two? Yeah, maybe. Not sure. Come on, draw my little lines here. All right, maybe like that. Really close, but not quite, is it? Not quite. Okay, so there's no such thing as almost. It's either yes or it's no. Well, this one's no. And since it's no, there are no number of lines of symmetry. And number three, what do you think? Really? No, no. Come on, make your line. Wow, this is getting frustrating. Like that? Oh, not like that. Yeah, like that. Well, I'm off center, but yeah. So, yeah, does have line symmetry, so the answer is yes. Are there any other lines of symmetry? I think just that one. Let's see. You think maybe no? Well, if that doesn't work, that won't work, right? Yeah. So just the one. So yes and one. All right. Any questions on line symmetry? Well, then let's see what they tell us about rotational symmetry. So rotational symmetry is back on page 654, and let's see what the definition is. It says a figure in the plane has rotational symmetry. I don't think anybody calls it radial symmetry. Has rotational symmetry if the figure can be mapped onto itself by a rotation between 0 and 360 degrees about the center of the figure, which is called the center of symmetry or point of symmetry. You know how we would have a point of rotation or the center of rotation? Well, center of symmetry or point of symmetry. So, for example, it says the figure below, which appears to be a square, has rotational symmetry because a rotation of 90 degrees or 180 degrees or 270 degrees maps the figure onto itself. See, let's see how that works. If I take a square and then I rotate that 90 degrees, well, doesn't that look identical to what I started with? And another 90 degrees, it's identical to what I started with. Another 90. So, look, the original 90, that was 90 degrees. Another 90, that's 180. Another 90, that's 270. And then look, 360 doesn't really count because when I've gone all the way around the circle, it better look like it started, correct? Okay. So, but here's the thing. So it does have rotational symmetry. And then there's some other things we want to be able to tell about rotational symmetry called order of symmetry and magnitude of symmetry. This is the number of times a figure maps onto itself as it rotates from 0 to 360 is called the order So what was the order here? Well, let's count them. 1, 2, 3, and then back to 4. Okay, yeah, I know. 360, it's got to be back to what it started with. So that counts, though, as the fourth one. You got to, otherwise you're hanging, right? You never get back around to where you started. You're stuck here. So you got to do that fourth turn to get back to where you started. So the order of symmetry for that one is 4. And then the magnitude, well, that's the degree measure of each of those rotations that maps the figure onto itself. So 90 degrees, 90 degrees, 90 degrees, 90 degrees. All right, so it's 90 degrees is the magnitude. Now here's something nice. If you can figure out the order, you can figure out the magnitude. Or if you know the magnitude, you can figure out the order, because the magnitude is 360 divided by the order. Or I like to think of it this way. The order times the magnitude equals 360. So 360 is constant. So if you know the order, you can solve for the magnitude. If you know the magnitude, you can solve for the order. 4 times 90 equals 360. It all works out. Order 4, magnitude 90 equals 360. Make sense? Okay. Well, let's stay there on page 654, and let's look at example 2 here. It says to state whether the figure has rotational symmetry, and then to write yes or no, and then we're supposed to try to figure out the order and the magnitude. And the center of symmetry will be the center of the polygon. And, you know, I'll give you a better definition of the center of the polygon. Well, I may have to get to it here in a minute, but we'll see. All right, so here's what I've done. Yeah, put that back. I took this and I copied it so that I could turn it, okay? So if I take this and I rotate it to there, it's identical. So that's 1. Do it again, that's 2, 3, 4, 5, and number 6 gets us back to where we started. So it does have rotational symmetry. So we write yes. The order is 6. Now, how many degrees at a time was I turning it then? Order times magnitude equals 360. So 6 times what equals 360? Yeah, 60. And the magnitude equals 60. All right, let me try something I wasn't really planning on here. The center of rotation. Let me make this a little bigger so it's easy to see. All right, the center of a polygon is actually the radius of the circle that we can circumscribe about the polygon. So I'm off just a bit here. Look at how close that is. All right, so that'll have to do. That's pretty good. So the center of this circle is also the center of the polygon. All right? So that's another clue to kind of help you out whether or not you're going to have some rotational symmetries. Can you visualize being able to do that? Okay, let's get rid of that. All right, back where we started. So then let's look at B. Does this have rotational symmetry? Well, let's see. I'll move it right over here. Tell me when it looks exactly like it was when we started. Tell me when it's mapped onto itself. Yeah, not until we get back to where we started. So we do not say order 1, magnitude 360. Instead, we just say, no, it doesn't have rotational symmetry. Okay? And then C, all right, so I copied this here. So tell me when it looks, I'll do it next to it so you can see it better. When they look identical. They're identical now. Nope, 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 nope. Oh, yes. They are, aren't they? So how many times? Let's see, let's start. So 1, 2. So the order is 2. So what do we write? We write yes. We write order equals 2. And if the order is 2, what does the magnitude have to be? Yeah, it has to be 180 because 2 times 180 equals 360. So the magnitude equals 180. Okay? Now in this case, that's not a polygon, so I'd have a hard time drawing a circle around that. So they found the center of it by drawing in the diagonals from the corners. Hey, I wonder if that would work with this. We drew in diagonals. That and that. And I draw in that other diagonal, it better intersect at the same place those two did, didn't it? And then that, man, I'm digging that. Then I can get my compass out, put it there, center, do that. I have a hard time going all the way around here. Let's move everything over some. Yeah, looky there. Works out just right, doesn't it? Okay. All right. So how we doing with rotational symmetry? What do you think? Yeah, I think so. All right, let's see, though. So back over to page 656, 4, 5, and 6. State whether the figure has rotational symmetry. Write yes or no. If so, you don't have to copy it, but you do have to state the order and the magnitude. So for number 4, let's see, I didn't make these easily rotatable here. Where's my camera going? So let me capture this. Hey, I don't know why those extra lines are there. It's weird looking. If I take that, does it look identical to the one I started with? No. No. And well, now it does. It's better, right? I'm back to literally back to where I started. So that didn't work out so well. So no, it does not have rotational symmetry. So no order, no magnitude. All right, well then, number 5. Let's see if I can duplicate this one. Again, I don't know why the little lines are there. All right, so they're identical now. Rotate. Yeah, they're identical again, except for the silly little line that's there. So that's 1, 2. So yes, does have rotational symmetry. The order is 2, and if the order is 2, the magnitude must be, that's right, 180. Okay, so far so good. All right, number 6. What do you think? Yeah, boy, it sure looks like it has rotational symmetry, so I'm going to go ahead and say yes. Now, you're not always going to be able to do what I do with taking a picture of it or duplicating with the software a figure that looks just like it. So let's visualize it. If I rotate this over to here, if this little triangle rotates over to this one, All right, that would be, now it would look exactly the same, right? So that's 1. And then couldn't I do it again? 2, again 3, again 4. So shouldn't the order be 4? Yeah, so if the order is 4, what's the magnitude? Yeah, so each of those rotations was 90 degrees. And then let's see if it does work out that way. Might as well test it since we can. Do it here. So, yeah, 1, 2, 3, 4, identical. All right. So the order is 4, which means the magnitude really is 90. Any questions? All right, now I'm going to throw a little extra learning at you here for three-dimensional figures, solids. We call things solids, any three-dimensional figure, we call it solids even if it's hollow. Like a basketball is a solid even though it's hollow. A wiffle ball is solid even though it's hollow. Football, okay, baseball, definitely solid. All right, now three-dimensional figures or solids can also have symmetry. And there's two types, plane symmetry and axis symmetry. Now, plane symmetry means this. A three-dimensional figure has plane symmetry if the figure can be mapped onto itself by a reflection in a plane. In other words, there's a plane that you can pass through the three-dimensional figure that literally cuts it into two halves. Okay? The half over here on the left is exactly the same size as the half over here on the right. Same size, same shape. They're congruent figures, three-dimensional figures. So that's plane symmetry. So the solid on the left could be mapped and look exactly like the solid on the right, vice versa. Okay? Axis symmetry is when a three-dimensional figure can be mapped onto itself by a rotation between 0 and 360 degrees. Okay? So, like a cone has axis symmetry. If you have a prism or a pyramid where the base is a polygon that has axis or rotational symmetry, then the three-dimensional figure is going to have axis symmetry. Now, here's what I'm talking about. If we look at example 3 on page 655, we'll see that for part A, that L-shaped prism, right? A prism is a three-dimensional figure made up of uh, polygons. Every surface is a polygon. And so that one has plane symmetry, but you got to cut the plane just right? You can't cut it this way. Can't do that. That plane's not going to do it. It has to be this one they drew here, which I don't really have the ability to draw. Not that talented. But it's got plane symmetry that way. And then look at B. I think this is sort of interesting. That this regular pentagonal prism has plane symmetry in the same way that the example A had. Okay? You can cut it, but now it's got to be a horizontal plane instead of a vertical one that does it. And it's got to be midway between the top and the bottom base of the prism. But you see here the green plane. You can cut it into two equal halves so it has plane symmetry. And then notice that the red line gives it axis symmetry. And notice what the red line does. It connects the center of that pentagon with the center of that pentagon. And since it's a regular pentagon, those pentagons would have rotational symmetry. So we could turn those, and in fact, it'd have an order of 5, right? And then its magnitude, what is 360 divided by 5? Anybody know? Really? Okay. All right. We good? All right. So let's make sure. Number 8. State whether the figure has plane symmetry, axis symmetry, both, or neither. Yeah, it's going to have both, right? Now, assuming that those are really rectangles, okay? We can connect the center of that one, the center of that one, make that our axis, and we can, and if they're squares, we can do it 4 times. If they're just rectangles, we can do it twice. And then, so that's how it has axis symmetry. How can it have plane symmetry? You can have a plane, cut it in 2. I tried to make it so that that's congruent to that. Didn't quite pull that off, but I tried to. Yeah, so it also has plane symmetry. So that one has both. All right, you guys with me? Okay. In your assignment on page 656, let's do 1 through 6, 8 through 33, 51 through 54, and 59 through 61. You don't have to, when it tells you to copy the figure, you don't have to do that, but do the rest. You know, tell the order, the magnitude, the number of lines of symmetry, you know, whichever applies.